Hello, physics. We are starting here, chapter 18. This is section 1, page 630, and it is on circuits and the circuit elements, or the things that make up a circuit. First of all, they talk about drawing a circuit, and drawing a circuit is called a schematic diagram. You may not hear that too much. You probably are more likely going to hear it called a circuit diagram, and you'll see that they say basically those are the same thing, a circuit diagram. So there's some symbols and so forth that are involved, and the first one is the simplest and perhaps the most confusing, and that is this little black line shown at an angle. Really, you'll see that there's a black line here, 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 and so on down the line, that there are black lines. Those black lines are just simply trying to show wires or conductors. You will see here in the homework diagram that these lines are drawn. These are to represent wires. As you can see in this diagram, here you've got curved wires, but whenever we show circuit diagrams, we always show them at right angles. Even though rarely are the wires going exactly in this path, we always show them at right angles, and that is why at the beginning here it shows that this represents a wire conductor at a right angle, even though the wire is probably curved. So the next element that they talk about here, or part of a circuit, is a resistor, and it is shown with a zigzag line, and this is a conductor on both sides, and the resistor is in the middle. There are many different kinds of resistors, and in fact a light bulb is another kind of resistor, and it is shown with that same zigzag line in between, but usually with something else to designate that it's a light bulb, and a circle, and it comes up like this. But you'll notice that it has the same zigzag line, trying to show that it is in fact a resistor as well. Plugs, not so often shown in circuits. So batteries are shown in a circuit with a big line and a little line. That represents one battery. We can do it this way to show many batteries. And even some batteries, like the 9-volt battery, is made up of several batteries inside of a battery to get the voltage up to 9 volts. Otherwise, a single battery is generally 1.5 volts. Even the big one is 1.5 volts. But you can combine them, and we will talk about that in such a way that you can make a 9-volt battery, and that would be designated like this, because you get several 1.5 volt batteries together. And this here is to represent a switch. The two circles with a line in between, that's a closed switch. Two dots or circles with like an open door is an open switch. Open switches do not complete the circuit, so no electricity goes through. That's why it turns off the lights. And the other one that's being shown here is a capacitor, which can be shown by two parallel plates, like it's drawn here, or this way. And here's just two plates. Here is a more likely device that you're going to see in an electrical circuit, where you've taken those two and you've kind of rolled them up so they take up less space. All right, next side here, a couple of concepts to toss in here. And we already talked about a circuit diagram, because an electrical circuit has to have a complete circle to go through. If you disconnect it anywhere, then the light will not work. So if it's connected and electricity can pass all the way through, it's called a closed circuit. If it has any part of it open, like we showed you with the switch, that's called an open circuit, and nothing will flow. Light bulbs won't turn on and so forth. Now, whenever a circuit has something on it that requires work, like a light bulb or a motor, we call that a load. If there is no light bulb in there, in the way, it can go from the battery right back to the battery. We call that a short circuit, and that's in your book here. Short circuit because it gets to take a shortcut, and there is no load, so the electrons can flow freely. It's kind of like breaking the dam of a lake. All of a sudden, all the water or all the electrons flow, and when all of them are flowing so much, then the little bit of resistance that is there creates tremendous heat and can melt the wires, melt the insulation, and of course can cause a fire. Whether or not the fire keeps burning is the question, but it will cause a fire or a spark, and sometimes so fast you can't even react to it. I encourage you to read this part here about CFLs and LEDs. CFLs are these compact fluorescent tubes, these curly light bulbs. These are probably going away because they do have mercury in them. They are more efficient than the traditional old incandescent light bulb, which is where we get this drawing from. These are incandescent light bulbs that just have a little resistor in between that lights up. We're getting away from these. Many places are now making them illegal. And we have gone to these CFLs, but we're more and more going with what's called LEDs. LEDs have been around for a while. Usually it's a little tiny thing that might be on your phone or on a computer and something that lights up a little dot, but we're using them more and more to light up entire rooms. They turn out to be much more efficient, generate less heat, and don't pollute the environment as much. Lastly, on this page here, EMF stands for electromotive force. Electromotive force, that is whatever is generating the electricity. Could be a battery, could be a generator, things that generate that force that pushes electrons. Without an EMF, there is no flow of electrons. In terms of water, it's like the pump for water. It pumps those electrons along. Interestingly enough, batteries themselves have a resistance. So even though that they are an EMF source, electromotive force source, they are also a resistor. So it's kind of surprising when you go to measure circuits later on. Here they're trying to show you that inside this battery, there's not only the battery, but there's a little bit of resistance as well. So the battery loses some of its energy just in producing energy. And it can mess up your calculations when you're doing circuit calculations. So we usually do calculations based on the voltage at the terminals of the battery, not what it actually has potential, because we're losing some of that there. So we just don't waste our time with it. And we disregard the resistance of the battery. All right, that's it for section 1.